So could you please tell us about yourself?
My name is Becnel. I'm a senior instructor at Louisiana State University in the mechanical engineering department. And before that, I was in the aerospace engineering department at the University of Maryland as a senior lecturer and have done that. So I've been teaching at the college level for the last year. And prior to that, I got my PhD and master's at University of Maryland in the aerospace department. And I've worked under Dr. Norman Worley, who was the chair, just stepped down from the chair's position of that department. And prior to that, I was in LSU, actually back at LSU in my kind of alma mater, home department in mechanical engineering. So I've had a lot of time spent in the university environment.
Mhm. So why did you want to become an aerospace engineer?
Well, it's so I would love to go to space. I wanted to be an astronaut when I was young and actually into college. I thought, surely I can become an astronaut. And then, that's very, very hard to do. But I knew that if I wanted to become a NASA astronaut, a higher degree, a master's or PhD is what is required for that. And I was interested in grad school anyway, so I pursued that. Always interested in aerospace engineering because things that fly have fascinated me. I started in mechanical engineering. Actually, was no aerospace engineering in Louisiana at the time. We have a minor now in our department, but they're really similar. So I played with Legos growing up, enjoyed kind of building model rockets and that kind of stuff. And like sciences, I was not the best at math. Gotten better at it, although it's still really, really tough for me. And just thought aerospace engineering would be an interesting career path to pursue. So because I was interested in things and science, I kind of discovered engineering was, I guess, applied science. And so I, early on in college, picked an engineering degree and then just kind of stuck with it.
So your work is primarily on smart materials and devices. So what are smart structures?
Sure. Smart structures is a big catch-all term that is thrown around a lot and means a lot of different things to a lot of different people depending on the areas that you are interested in. But since I'm an aerospace engineer, whenever we talk about smart structures, really what we mean is just something that serves a structural purpose or provides some sort of mechanical function and also does something else. Usually it is the smart structure has some feature or some material or some design component to it that makes it function as what we call a sensor. So it can, measure temperature or displacement or position or something like that, or an actuator, which it causes a change either in displacement or outputs of force or changes electrical resistance, or both. And so anytime I talk about a smart structure, making something that is multifunctional, so a part or a piece of something that is a structural component, but also adds some more information or some more control. I'm trying to think of an example because even that description is pretty abstract, but think of something. Oh, okay. So like a seat belt, for example, right? A classical seat belt is something that's designed. It's a mechanism that basically keeps you from moving. That's how it's designed, or it keeps you from moving too quickly. So when the seat belts in your car get activated in a crash, really what happens is the mechanical components inside the seatbelt lock up, and then there's a little metal pin inside there, and the mechanical components actually twist that pin, and twisting that pin dissipates a bunch of energy. So instead of you going forward and carrying all that kinetic energy forward with you, the seatbelt shoulder strap stops you, and that kinetic energy gets converted into twisting this pin. And so that's how a seatbelt kind of slows you down gradually, so you don't, fly through the windshield or something. So a smart structure that you might apply to a seatbelt. The seatbelt still functions the same way, or a similar, outcome is that it slows you down, but maybe it senses how big of a person is sitting in the seat, or it senses how strong a crash you're, going through at that moment. And so it would adjust its behavior to do better than just what we would call a dumb seatbelt, right? It's a smart seatbelt. So it knows something more. It's designed to do better based on some information that it's programmed to use, or it collects itself, or something like that. So yeah, that's an example of a smart structure that I just made up off the top of my head.
So how can smart structures protect the crew of a spaceship, for instance?
Yeah, sure. So a seatbelt would be a great example, but what I worked on in my master's thesis and then into my PhD was energy absorbing devices. So we call these, shock absorbers, basically. So like the shock absorber in your car suspension isolates you from a bumpy road, let's say. And so you just springs, metal springs, leaf springs in your car, and then some kind of piston and cylinder, like hydraulic or pneumatic shock absorber that kind of dissipates that bouncing energy. But more modern cars and most cars today use active suspension systems that kind of sense the road conditions and then will adapt to how bouncy or what the speed is or how many people are in the car. So I was looking at solutions that could help with, at first, helicopter seats, so protect pilots and crew members from injury during a helicopter crash. The University of Maryland is a rotorcraft center of excellence, so they have a lot of helicopter research there. So that's how I got wrapped up in helicopters. And then I was always interested in space flight. And so I expanded that research to apply to spacecraft. And really the only difference there is weight. Like heavy objects are even more of a problem if you're trying to send them to space. So obviously you don't want your helicopter seat to be heavier if you can help it, but you really, really don't want your spacecraft seat to be heavy, because it's, that times like north of $10,000 per pound, let's say, to get something to orbit. So every pound you could saved a lot of money. And so to protect a crew from a spaceship crew from injury, I was looking at the different phases of spaceflight. So you have the launch, where on launch there's a lot of vibration that comes from the rocket engines, and so shaking the crew in their seats is something that you want to protect against. For example, your eyeballs moving inside of your head if you have a hard time seeing instruments, and kind of having situational awareness that might make it more dangerous. Also, it's uncomfortable. And so the energy absorbers that I was working on, the smart structures that I was working on, were adaptive. They could be tuned to that vibration environment, and the individualized astronaut's weight and the launch vibration profile could all be designed into the system to give you, what we call an optimum performance or isolation of vibration. And then whenever you come back to Earth from orbit, you enter the atmosphere, and there's a lot of acceleration or deceleration that you experience. And then if you land under parachute, then you're your parachutes, drop you down pretty gently, but when you hit the ocean, or maybe you have to land on the surface of the earth instead of on the ocean, then it would be a different type of impact. And so the smart structures that we were talking about, these energy absorbers, would also adapt to whether you're landing on the water or landing on land. And basically, practically that means seat can stroke a certain amount to dissipate the energy, let's say over this distance. And you want to use the full distance, no matter if you land in the water or on the surface of the land. And so changing the energy absorber profile in response to that you're having is what my research looked at. So really, we're talking about protecting the crew of spaceship from what we think of as the dynamic environment. So vibration and shock and all these kind of rough handling of the people inside.
So what are the applications for smart structures in crew garments?
That's an interesting question, and I think again it kind of it depends on how you're defining a smart structure, but I define it as a mechanical or an aerospace engineer is kind of some material or some arrangement of materials that would make the crew more comfortable. So in the case of a crew garment, one of the problems with spacesuits is that, so we're talking about the extravehicular activity suits, the EVA suits, the big bulky white spacesuits that you see astronauts outside of the space station, and those are pressurized spacesuits. You have the vacuum of space, which people cannot live in, and so the spacesuits that they are in whenever they're outside of the spaceship, they're pressurized themselves so that the people are safe inside of them. But when you have a fabric spacesuit that's pressurized, it's like a balloon. And so the astronauts that are working on EVA inside of these pressurized suits, it's really exhausting. And so, think about being kind of inside an inflated balloon, and then every time you want to maybe you want to like bend your arm or something, so that bending motion in your arm, naturally an inflated balloon wants to have your arm straight out, or maybe the suits are designed to have like a neutral pose like this. So anytime you're bending your arm away from it, you're really like stretching this suit away from its natural shape, and so it's really exhausting. The gloves, even the fingertips and the gloves basically want to be straight all the time. And so if you want to grab a wrench or something like that, you have to have a lot of hand strength and conditioning, or your grip will fail, and you won't be able to hold on to the wrench or something like that. And if you look at pictures of astronauts' hands after 4 or 6 hour EVA activities, they'll like lose their fingernails, and they get these really nasty calluses and hand injuries basically from this really exhausting kind of fighting against the spacesuit. And so a smart structure applied in that scenario could be something like I worked on a glove that had some 3D printed material components to it. So if you imagine just a regular glove that has some components that are maybe printed around the joints in the fingers, there's some design and some material that runs along the top surface of the finger, and if you bend your finger, that material would stretch, right? That distance on the top of your finger gets shorter when it's line, and then when curved it gets longer. So that's a change in distance. And so the smart structure, the 3D printed spacesuit glove idea that we were looking at for smart structures is if you make this material or this 3D printed material smart structure, sense that the astronaut is trying to bend their finger to grasp something, to grip a tool or something like that. Then if you couple that maybe with a motor or some other actuator device, you can have almost like a robotic assistive grip. So it senses that they're trying to close their hand, and it would then stick to a motor or something like that that would help the astronaut close their hand, so that it's not all the human strength limitation, but it's taking what the human is trying to do and then assisting them to do that. So that's one application. And structure, kind of, because it's sensing what the astronaut's trying to do and then helping the astronaut do that. And there's all kinds of stuff like that. I mean, not just a glove, but any component in a spacesuit or a garment where the person is trying to accomplish some movement, but is hindered in doing that by some something in the system. Then you could apply smart structures to try and help make it easier for them to do that.
You also work in the manufacturing side of these smart materials. What are some of the problems that face the production of these structures?
Yeah, so right now, the way most of our smart devices, smart structures are made is really a lot of manual labor. So, that 3D printed glove project, I described it as a glove with some 3D printed components, and that's really what it is. I mean, you would like to imagine that with like now they're magical devices, and you can just have the printer make a full, complete working smart structure like this glove. But in reality, that's not how it works. It would be really hard to print a glove that's comfortable, first of all, because a glove, it's hollow on the inside, and so the way printers are limited currently is you can't print on top of nothing. So you have to have some infill material, and then removing that is a challenge. But in any case, the challenge with making these, the concepts for them are a lot more straightforward to arrive at than actually making the devices. So that glove, we started out with a glove that you buy at the store, and that's comfortable, and that's something that people are used to wearing. And then on top of that, we had to attach these 3D printed components and then manually connect the wires, the electronics, and then route those somehow up the back of the glove and feed it into an Arduino, which is a little micro, a single board computer that can take in sensing information from the 3D printed material and then command the motor to do that. So it's still, it's a complicated system, and it's supposed to fit on the back of a glove, let's say, and then that's something that requires manual labor, basically. So there's somebody that has to have the expertise and the skill and the artistry to build that from scratch. So when we talk about manufacturing smart devices or smart materials, it's really not like automated manufacturing at all. It's not like something that would come off of an assembly line. There's still a long way to go before a lot of these things are built in factories or anything like that. The other issue is that a lot of the materials that we use for them, so for example, the 3D printed material that was on the back of that glove, it would sense the change in length, and you would measure a change in the resistance. So the electrical resistance would change as the length of that 3D printed smart glove component would change. And so that material was something that we bought off of Amazon, but there's no quality control over that stuff. It's a lot of hobby or what we were using was a lot of hobby grade, like 3D printer plastic material. And what we really needed was uh, really good control over all of the um, what we call feedstock. So all of the plastic and the conductive particles that were added together to use material. So we started making our own, and then that's another challenge, right? You have to start making your own and keep track of all the process parameters that go into making that. Hi, come on in. Yeah, it's okay. That's one of the challenges when you talk about manufacturing. The materials is actually getting them. Hi, thank you. Because it's still really early. It's not like you can go to Home Depot and you can buy screws and bolts and nuts and pieces of metal that are cut to a certain size. But when you're making smart materials, it's all like starting from scratch, and so you have to make the materials themselves, and then you have to build things with them. So it's really starting from the ground up is one of the challenges.
It was also mentioned that you can use these smart structures and materials to improve human device interfaces. What are those devices and how can they improve using smart structures and materials?
Yeah, so that glove idea was one of the concepts that we had. Right now, I'm working at LSU to improve football helmets. We have hopefully going to get some grant money to look at better padding for the inside of football helmets to alleviate some of the problems have been studied with like traumatic brain injuries that football players experience when they get concussions. So trying to think of better or different ways to diminish the severity of impacts that football players experience. So that's a football player wearing a helmet, but anytime you have people working with machines or with hard, rigid equipment, then it's an unfortunate fact that the people are kind of the soft, squishy things that you have to protect all the time. So whether it's human space flight or automobile safety or sports safety, it's always about protecting the people, and it's a real challenge because it turns out people are relatively soft and squishy compared to all the other things, airplanes and spaceships and helicopters and football helmets, all of that stuff.
So what has been your toughest accomplishment so far?
I don't know. I mean, years ago when I was in grad school, was definitely getting sticking with the PhD was a real challenge. It's very rewarding, but it's also can be kind of lonely. The pursuit of a PhD is an individual activity because you are basically supposed to become an expert, or you're supposed to become the expert in whatever it is you're studying. So after a while, I didn't have anybody that I could talk to about problems that I was having with my research because nobody knew about it. And even my advisor that I was working for, that was kind of my mentor still is my mentor, but was my mentor for a long time in my academic career. After a while, the last year or so of my PhD, I was working all by myself because any problems I had, I could ask, for help, but ultimately they didn't have much advice to give me that I hadn't already considered or wasn't new information. So that was a challenge. And, I'm like most engineers, it's still really lonely whenever you're working on something for months and months and months, and you're the only one that is doing it. So that's definitely a challenge. And it was a rewarding accomplishment to be finished with it. It's also, is definitely a challenge. And then the other, I don't know, accomplishment that I've come to appreciate more recently is deciding or finding a career in the university environment that I really enjoy. So I really enjoy working with students and teach classes. That's kind of my primary role here at LSU, is teaching classes. I get to do research, but it's secondary to my teaching responsibilities. And so that's really nice, but it's also something that was unexpected. I thought I would be working at SpaceX or NASA or something like that. And I had a few jobs that were like that. So engineering, consulting, and doing design work on small projects and stuff like that. But that environment, working on things, was not as appealing to me. And so the last few years I've kind of come to appreciate and recognize as an achievement just the recognition that I enjoy working with people and students in particular. I don't want to say gainful employment. I was always well compensated for my job, but finding a career that I felt like was kind of really valuable and something that I was proud of was also an accomplishment, I would say.
So what is a big milestone that you're looking forward to in your research?
I don't know. The next one, I guess, is a good answer. That's the fun thing about research, is that there are always new avenues to pursue. So as soon as, I'm excited about working on this football helmet project. I hope we're able to do something there. And then after working on a problem for long enough, you start to realize, oh, but what if we did this? Or what if we did this? Or like there's all these other new exciting possibilities that you never would have been aware of unless you started trying to solve the original problem. So I guess what I look forward to the most is just kind of the next exciting application of my background, my expertise in smart structures. But back when I was in grad school and working on helicopter and spacecraft seats, I wasn't doing anything with 3D printing. And now most of what I do is with 3D printing and new materials for 3D printing materials. So I imagine in the next 5-10 years, probably be something else that I come to, be engaged with and pursue because I'm interested in that. A new flavor of 3D printing or something else altogether. I don't know. Recently gotten into woodworking, so maybe I'll just start building wood instead of plastic and metal.
And lastly, to high schoolers like me and to younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
I think now is a really, really exciting time to be especially interested in aerospace engineering. I mean, I think all science and technology, I'm biased, obviously, because that's what I'm interested in, that's what I teach. But I think science and technology in particular are very interesting, and even more so now with the challenges that we are all trying to solve using science and technology are very massive and can be scary if you let them become too big to handle. But the fact that climate change and global warming is having such a big impact on people's lives and an increasingly important impact on people's lives, I think that a lot of really important and really meaningful work can be done by young people. And I'm almost 20 years out of high school, and when I was in high school, I didn't imagine that you could go work for like a electric car company, or SpaceX did not exist yet. I think they started in like 2005 maybe. So when I graduated, SpaceX didn't exist. They had just flown the first Virgin Galactic Spaceship One was flown in 2007, I think. And in any case, that was like the first time a person had gone to space who was not a civilian astronaut or a military astronaut. This was just a pilot who flew to the edge of space and back. So I was really excited about that challenge. Getting people off of the planet is my own personal challenge that I was always motivated by. I see so many other very compelling challenges that young people, high school students and early college students, can get involved with and really make a big impact. And the fact that it's easier than ever to learn all of this stuff, because the internet has made education and kind of the accumulation of knowledge so much faster than it ever was before. The fact that you can watch YouTube, if you're watching the right YouTube videos, you can learn the equivalent of a college degree, right? You can take courses from MIT and Stanford and all of these other world-renowned places for free on YouTube, because they make them that way. And you may not get a degree or a piece of paper that says that, but you learned it and you know it, and you can apply it, and you can do whatever you want with that knowledge. It's really exciting. If you see a problem that you want a solution to, you have more access than ever to the types of knowledge that will help you solve that problem. So I think that's anybody who's interested in becoming an aerospace engineer has an amazing, probably next 30 to 50 years to look forward to. I think we'll probably be on Mars in the next 5 years at least, which is a crazy thing to say, but I truly believe we probably will land in the next 5 years and on Mars. I'm interested in aerospace. There's all kinds of other cool stuff to do with climate science and computer resources, autonomous vehicles, and artificial intelligence, and all kinds of other stuff. So I would say pick a problem or a set of problems that you care about and use that as your guidance as to what you should study. If you're trying to learn how to solve a problem that you really care about solving, then it's so much easier to put up with all of the frustrating headaches that come with learning something new.
All right, well, thanks for coming on, and thanks for letting me interview you. That was great.
Sure. Yeah. Thanks a lot, Balamir.
Yep.
Have a good day.
You too. See you.